Imagine a journey to one of the most enigmatic moons in our solar system, a place with a hidden ocean, where life as we know it might just exist. In the next few minutes, we'll embark on an extraordinary adventure to Europa, uncovering the incredible challenges and innovative solutions required to send humans to this distant world. And stay tuned until the end, where we'll reveal a surprising discovery that could change everything we know about life beyond Earth. Our fascination with Europa began with robotic missions like Galileo and Juno, and soon the Europa Clipper will pave the way for humanity's next giant leap. In 2024, NASA is launching the Europa Clipper mission, a spacecraft designed to conduct detailed reconnaissance of Europa's ice shell and subsurface ocean. Scheduled to arrive at Jupiter in 2030, the Europa Clipper will perform over 40 close flybys of Europa using an array of sophisticated instruments to scan the moon's surface and probe its hidden depths. But what will it take to send humans to this icy moon orbiting Jupiter? Europa, a moon of Jupiter, is about 390 million miles from Earth. The journey alone will take approximately 6 years. Our goal, to explore Europa's ice-covered ocean and search for signs of life. But the challenges are immense. From the harsh radiation of Jupiter's magnetosphere to the extreme cold and the thick ice crust, every step of this mission requires groundbreaking technology. Planning a mission to Europa starts with meticulous preparation. Timing the launch is crucial. Our best window is when Earth and Jupiter are optimally aligned, minimizing travel time and fuel requirements. Once launched, our spacecraft will embark on a 6-year voyage using gravity assists from Venus and Earth to gain speed. Europa orbits Jupiter at a distance of about 417,000 miles, which is 671,000 kilometers. That is roughly 1.3 times the distance from Earth to the Moon. It takes Europa about 3.5 days to complete one orbit around Jupiter. Here's the fun part. Europa is tidally locked with Jupiter, which means the same side of Europa always faces the planet, much like how we only see one side of our moon. Europa formed around 4.5 billion years ago, alongside the rest of the solar system. It came together from the leftover gas and dust swirling around after the Sun formed. Jupiter's strong gravity played a significant role in shaping Europa and its fellow moons. It has a crust made of solid water ice that's about 10 to 15 miles, 15 to 25 kilometers thick. Beneath this icy shell, scientists believe there's a vast salty ocean. This ocean might be up to 40 to 100 miles, 60 to 160 kilometers deep, way deeper than any ocean on Earth. Beneath the ocean, Europa likely has a rocky mantle and a metallic core, similar to Earth. This moon sits within Jupiter's powerful magnetosphere, which is essentially a bubble of magnetic field created by the giant planet. Europa's own magnetic field is weak, but it interacts with Jupiter's magnetosphere in fascinating ways. Our spacecraft is a marvel of engineering designed to withstand the journey and protect its crew from radiation. Inside, a rotating habitat module will create artificial gravity, ensuring the astronauts can stay healthy and strong. Advanced life support systems will recycle air and water, and shielded compartments will provide safe havens during intense radiation exposure. Meet our crew: geologists, biologists, engineers, and doctors, all trained to conduct scientific experiments and handle emergencies. Their mission: to land on Europa, drill through its ice shell, and explore the ocean beneath. During the 6-year journey to Europa, survival will depend on rigorous preparation and advanced technology. Let's dive into the details of how our brave crew will endure the long voyage. The spacecraft is equipped with cutting-edge life support systems that recycle air and water. The Environmental Control and Life Support System, ECLSS, will continuously purify the air, remove CO2, and ensure a steady supply of oxygen. Water recycling systems will reclaim wastewater, including urine, through advanced filtration and purification processes, providing clean drinking water. Astronauts will need a reliable and nutritious food supply for the entire journey. A combination of pre-packaged meals and hydroponically grown fresh produce will sustain the crew. Hydroponic systems will allow the cultivation of vegetables in space, providing essential vitamins and minerals while also contributing to psychological well-being. One of the biggest challenges in deep space travel is protecting astronauts from harmful cosmic radiation. The spacecraft's design incorporates thick shielding, particularly around living quarters, using materials like polyethylene, which effectively blocks radiation. Additionally, water tanks surrounding the habitat module add an extra layer of protection. In case of solar storms or heightened cosmic radiation levels, the spacecraft features designated safe havens with enhanced shielding. Astronauts can take refuge in these compartments until radiation levels drop to safer levels. Maintaining physical health is crucial during long-duration missions. The spacecraft is equipped with exercise equipment such as treadmills, stationary bikes, and resistance machines. Astronauts will follow daily exercise routines to prevent muscle atrophy and bone loss caused by prolonged weightlessness. Isolation and confinement can take a toll on mental health. To combat this, the crew will have access to virtual reality environments that simulate Earth-like settings, providing a psychological escape. Regular communication with family and friends on Earth, along with group activities and hobbies, will help maintain morale. The time delay for radio communication between Earth and Europa ranges from approximately 32 minutes at the closest approach to 54 minutes at the farthest distance, with an average delay of about 43 minutes. These delays mean that real-time communication is impossible, and mission control must plan accordingly, relying on autonomous systems and pre-programmed instructions for immediate decision-making by the spacecraft and astronauts on Europa. The crew comprises experts in geology, biology, engineering, and medicine, each chosen for their skills and ability to work as a cohesive team. Extensive training in conflict resolution, stress management, and emergency procedures ensures they are prepared for any situation. Before departure, the crew will undergo extensive training in simulated missions, replicating the spacecraft environment and mission scenarios. This training will help them adapt to the challenges of long-duration spaceflight and fine-tune their problem-solving skills. A human-crewed spacecraft to Europa would weigh significantly more than the Juno mission, resulting in increased travel time. Using today's most powerful rockets, it would take at least 5 years to reach Jupiter, with a conservative estimate suggesting a one-way trip of 6 years for a spacecraft 3 times larger than the Apollo missions. A round trip, therefore, would take about 12 years, making it impractical due to the immense amount of supplies required, which would further increase the spacecraft's weight and travel time. To make the journey feasible, a strategy involving intermediate stops at bases on the Moon, Mars, and Ceres is proposed. These bases would allow the spacecraft to refuel and resupply, reducing the weight it needs to carry at any given time and enabling faster travel. In this scenario, a spacecraft could potentially reach Europa in just 1.5 years, stopping at these bases to refuel. However, several challenges remain. The absence of established bases on these celestial bodies, the necessity for planetary alignment for efficient travel, and the difficulty in ensuring alignment for the return journey, which might require astronauts to wait several years on Europa before returning to Earth. Arrival at Europa cut to the spacecraft approaching Jupiter, then zooming in on Europa. After 6 years of travel, the spacecraft finally arrives at the Jovian system. The next phase of the mission presents a series of critical maneuvers and challenges as we approach Europa. The spacecraft performs a complex series of orbital insertions to enter Jupiter's orbit. This requires precise calculations and careful execution to navigate the intense gravitational forces and radiation belts of the gas giant. Jupiter's radiation is a significant hazard. The spacecraft will spend limited time in the most intense radiation zones using a highly elliptical orbit to minimize exposure. Each flyby of Europa will be timed to ensure the spacecraft quickly moves out of these dangerous regions. Identifying safe zones. Using data from the Europa Clipper and other robotic missions, scientists have identified potential landing sites on Europa's surface. These sites are chosen based on safety, scientific value, and the potential for accessing subsurface water. Europa's surface is a mix of smooth ice plains, chaotic terrain, and potential ice spikes near the equator. High-resolution imaging helps pinpoint the safest and most scientifically promising landing zones. The lander will be equipped with advanced autonomous systems to navigate and land on Europa's surface. Without an atmosphere, traditional parachutes are ineffective. Instead, retro rockets will slow the descent, and a sophisticated terrain relative navigation system will guide the lander to a safe touchdown. Given the potential hazards, the lander must execute a pinpoint landing. High-definition cameras and LiDAR sensors will scan the surface in real time, allowing onboard AI to make last-minute adjustments and ensure a precise and safe landing. Upon landing, the first task is to deploy the habitat module. This self-sustaining habitat will provide living quarters, laboratories, and a safe environment for the crew. Reliable power is essential. The habitat will be equipped with nuclear power sources, providing a steady supply of energy for life support systems, scientific equipment, and communication with Earth. With the base established, the crew will begin drilling operations to penetrate Europa's ice shell. Using a nuclear-powered drill, they will bore through the ice, potentially reaching the subsurface ocean. This operation could take weeks to months, depending on the thickness of the ice. Once access to the ocean is achieved, a submersible will be deployed to explore the watery depths. Equipped with cameras, sensors, and sample collection tools, this submersible will search for signs of life, particularly around hypothesized hydrothermal vents. Samples collected from the ice and ocean will be analyzed in the on-site laboratory. Advanced instruments will search for organic molecules, microbial life, and other signs of biological activity, sending data back to Earth for further study. After months of exploration, it will be time to return home. The spacecraft will lift off from Europa, rendezvous with the orbiting mothership, and begin the long journey back to Earth. The samples and data collected will keep scientists busy for decades, unlocking the secrets of Europa. During their mission, our astronauts discovered organic molecules in Europa's ocean, complex compounds that are the building blocks of life. This discovery doesn't just hint at the possibility of life on Europa, it opens up new avenues for finding life elsewhere in our solar system and beyond. The journey to Europa is more than a mission. It's a quest for knowledge, a testament to human ingenuity, and a giant leap towards answering one of humanity's most profound questions. Are we alone in the universe? Thank you for joining us on this incredible journey. If you're as fascinated by the possibilities of exploring Europa as we are, don't forget to like, share, and subscribe for more exciting space exploration content. Until next time, keep looking up at the stars and dreaming big.